Hello to everyone. Welcome to the course on numerical linear algebra and application. Today we are going to learn 50th lecture of this course, 10th module. Today's lecture we are going to do some worked out examples where you feel comfortability in solving the matrix problems like power method, similarity transformation and iterative procedures. The first and foremost example which we wanted to do is the power method. All of you knowing power method we use for finding out the largest eigenvalue of a matrix, or you can call it as dominant eigenvalue of the matrix. Let's say this matrix has 3 rows, 3 columns. 1 2 0, minus 1 minus 2 1 0 2 1 3 1, and let's say the starting vector given as x naught as 1, and this is x1 of 0th iteration 1, and this is x2 of 0 is 1. So all three initial vectors are given. Now I apply the algorithm of power method for the matrix A. Look at this first matrix iteration. If you look at A times of x naught, you know A is 3 by 3 matrix, and this is a 1 column 3 rows 3 by 1. So ultimately I do get as 3 by 1, 3 rows 1 column. So 1 into 1, 2 into 2, 3, that is 3, minus 2 into 1, minus 2, plus 1, plus 2. So it is ultimately plus 1. 1 into 1, 1, 3 into 1, 3, 1 into 1, 1. So 3 plus 1, 5. And look at this. In this, the bigger value is 5. So what I do is I will divide with 5. So it is 3 by 5, 1 by 5, 5 by 5. So 3 by 5 is 0.6, 1 by 5 is 0.2, and 5 by 5 is 1. In the second iteration, I get the matrix, this matrix, this matrix, this matrix, multiplied with x1, 0.6, 0.2, 1. So 1 into 0.6 plus 2 into 0.4, that is 1, minus 2 into 6, that is minus of 1.2 plus 0.2 plus 2. So that is 2.2 minus 1.2, that is 1. Third iteration is 0.6 plus 0.6 plus 1. So that is 1.2 plus 1, which is equal to 2.2. That is fine, 2.2. The second iteration. Look at this. In the first iteration, what you get is 0.6, 0.2, 1. Second iteration it is 1, 1, 2.2. And by scaling among these, you see here the largest value is 2.2. So you divide with 2.2, right? So you divide with 2.2. So when you divide with 2.2, 1 upon 2.2, this is 4545 point, and when you divide with 1 over 2.2, it is 0.4545, and divide with 2.2, this is 1. So in the iteration 3, that is 1 2 0, minus 2 1 2, 1 3 1, multiplied with 0.4545, 0.4545, 1. So 1 into 0.45, so it is 0.4545 plus 2 into 0.4545 plus 0, which turns out to be 1.3636. Second one is minus 2 into 0.4545 plus 1 into 0.4545 plus 2 into 1, which turns out to be this and third one is 1 into 0.4545 plus 3 into 0.4545 plus 1 into 1, which turns out to be this 2.8182. Look at this, and by scaling in this 2.8182 is the bigger value, so you divide with that. So when you divide with that, that is 1.3636 divided by 2.8182, which will give you 0.48439. So if nothing is told, we assume that 4 significant digits is enough. Then 1.5454 divided by 2.8182, which is 0.5484. Then 2.8182 divided by 2.8182, which is 1. So this is the matrix, you do get it. In the iteration 4, so that is AX3, that is 1, 2, 0, minus 2, 1, 2, 1, 3, 1, multiplied with 0.4839, 0.5484, 1. So 1 multiplied with 0.4839 plus 2 multiplied with 0.5484 plus 0, which turns out to be 1.5806. In the second matrix, minus 2 into 0.4839 plus 1 into 0.5484 plus 2 into 1, which turns out to be 1.5806. Third one is 1 into 0.4839 plus 3 into 0.5484 plus 1 into 1, which turns out to be 3.129 in the fourth iteration. So what is the bigger value here? Bigger value here is 3.129. So we divide with 3.129, which is 1.5806 divided by 3.129, which turns out to be 0.5052. Second one is 1.5806 divided by 3.129, which is 0.5052. Third one is 3.129 divided with 3.129, which is 1. So essentially after 4 iterations, you do arrive 0.5052, 0.5052, 1. So in the fifth iteration, AX4, that is A is 120 minus 212 131 multiplied with 0.5052, 0.5052, 1. So then it is 1 into 0.5052, which is 1.5155. Second one is 2 into minus 2 into 0.5052 plus 1 into 0.5052 plus 2 into 1. So that is 1.4948. And second one is 1 into 0.5052 plus 3 into 0.5052 plus 1 into 1, which turns out to be 3.0206 after 5 iterations. So after 5 iterations, we could able to arrive to this solution. Now if you make into, so the bigger value out of which is 3.0206. So if you divide with 3.0206, which is 1.5155 divided with 3.0206, which is 0.5017, and 1.4948 divided with 3.0206, 0.4949, and 3.0206 divided with 3.0206, which is 1. So yes, you get after 5 iterations this. And if you do it AX5, and A is the matrix, so it is 1 into 0.5017 plus 2 into 0.4949 plus 0. So which will give you this entry. Second entry is minus 2 into 0.5017 plus 1 into 0.4949 plus 2 into 1. This will give you this. And third one is 1 into 0.5017 plus 3 into 0.4949 plus 1 into 1, which will give you this one. So essentially you will have 1.4915, 1.4915, 2.9863. This is the one which you derive after 6 iterations. And out of this, the bigger value as it appears, it is 2.9863. So if you do it 2.9863, so that is 1.4915 divided by 2.9863. 1.4915 divided by 2.9863. 2.9863 upon 2.9863, you will get 1. So the first element is 0.4994, second one is 0.4994, third one is 1. So you get this approximation. And when you multiply with AX6 as per this algorithm, 1 into 0.4994 plus 2 into 0.4994 plus 0 into 1. So which we allow this one, 1.4983. Second one is minus 2 into 0.4994 plus 1 into 0.4994 plus 2 into 1, which will give you this. And third one is 1 into 0.4994 plus 3 into 0.4994 plus 1 into 1. This will give you this. So out of these three, the bigger one is 2.9977. So which is, when you divide with 2.9977, 1.4983, 1.5006, 2.9977. So when you divide with 2.9977, which turns out to be 0.4998, 0.5006, and it is 1. So the dominant eigenvalue lambda is equal to, that is 3, that is the factor which you get it, lambda, that is, and the dominant eigenvector is 0.4998, which is close to 0.5, 0.51. So after 7 iterations, so you do get dominant lambda eigenvalue is 3 and dominant eigenvalue is, that is, eigenvector is, that is 0.50, 0.501. And in the second example, use the power method with scaling to approximate a dominant eigenvector of the matrix. That is, this is the matrix -1, -6, 0, 2, 7, 0, 1, 2, -1. Start with x naught is equal to 1, 1, 1 and calculate 6 iterations. Then use x4 to approximate the dominant eigenvalue of A. So in the iteration 1, so you will have -1, -6, 0, 2, 7, 0, 1, 2, -1 multiplied with 1, 1, 1. So you get -1 into 1, -1, -1 into 1, -1, -6 into 1. So it is -7. And it is 2 into 1 plus 7 into 1 plus 0. So it is 9. Third one is 1 into 1, 2 into 1, -1 into 1. So it is 2. So at the end you do get as -7, 9, 2. And by scaling we obtain the approximation like this. So x1 is equal to, bigger value is 9 as we seen over here. So when you divide with the bigger value 9, so -7 by 9, 9 by 9, 2 by 9, which is minus of 0.7781 and it is 0.222. So in the second iteration you multiply with AX1. So this is the matrix, 3 by 3 matrix, and you multiply with this. So it is -1 into minus of 0.778 and -6 into 1 plus 0. So this is the matrix. And in the second iteration is 2 into minus of 0.778 plus 7 into 1. So you get this. And third one is 1 into minus of 0.778 plus 2 into 1 minus 1 into 0.222, etc. You arrive this. So ultimately you do get minus of 5.2222, 5.444, and it is 1. and by scaling you see the bigger value is 5.4444, so you scale it. X2 is 1 by 5.444, so when you divide with this vector you do get as 0.9592 and it is 1 and it is 0.1837. So you do get iteration 3, AX2 is equal to minus 1 6 minus 6 0 2 7 0 1 2 minus 1 multiplied with this vector, that is minus of 0.9592 1.1839. So you get minus 1 into minus of 0.9592 minus 6 into 1, so you arrive this value. And second value is 2 into minus of 0.9592 plus 7 into 1, you get this value. Third value is 1 into minus of 0.9592 plus 2 into 1 minus 1 into 0.1837, you get this value. So this is the matrix you do get. And by scaling out of this, the bigger value is this bigger of 5.0816. So 5.0816, when you divide with this, first value by this you get minus of 0.992, second value by this you get 1, third value by this you get this value. And in the fourth iteration AX4 you get matrix A, and this is the value which you get it. So minus 1 into minus of 0.992, second value is 2 into minus of 0.992, 7 into 1, you get this value. Third value is 1 into minus of 0.992, 2 into 1 minus 1 into 0.1687, you get this value. So this is the fourth iteration. So when you write this scaling by appropriate action, x4 is equal to 1.501046 and you scale it, so you get 0.9984 and 1 and last value is this. Similarly, when you continue this fifth iteration, so it is minus 1 into minus of 0.9984 plus minus 6 into 1 plus 0, it goes anyway. So the value turns out to be this value. Similarly, second iteration you get as 2 into minus of 0.9984 plus 7 into 1 plus 0. So similarly, third value is 1 into minus of 0.9984 plus 2 into 1 minus 1 into 0.01673. So ultimately you will end up with this value after 4 iterations, right? And approximate this value x5 is 1.50032. So when you divide with this matrix column vector, so ultimately you will end up with this value minus of 0.9997 and 1.1667. Therefore, the dominant eigenvalue lambda is equal to 5.00 is, that is approximately 5, and the eigenvector corresponding to this is this vector, which is approximately minus 1, 1 and 0.17. So like that we can continue for several iterations. So definitely you will be getting the much more closest best approximation. Similarly for you, if you look at the successive relaxation method, for example 3x minus y plus z is equal to 1 and minus x plus 3y minus z is equal to 7, this is the one. Suppose you are given this vector as 0 0, that is x0 of 0 is equal to 0, y0 of 0 is equal to 0, z0 of 0 is equal to 0. Somehow you get the first initial approximation if not given, and then you continue the what you call successive or relaxation parameter with some relaxation parameter value omega. We know that for symmetric positive definite matrix, the SOR method converges for all values of the relaxation parameter omega from the interval 0 to omega, that is 0 less than omega less than or equal to 2. The iterations of the SOR method is, there are actually 3 equations. If you observe very closely, let's see trial and error, what would happen? Suppose y is equal to 2, y is equal to, let's say 2, right? So y is equal to 2 and x is equal to 1. x is equal to 1, y is equal to 2 and z. So it becomes very difficult to guess. So anyway, these are the three equations given. You try to see that how they would be changing. From the above equations, what we do is, I would like to write first equation 3x minus 5 minus z is equal to 1 as x is equal to, the scheme is xk plus 1 is equal to 1 over 3. The coefficient of xk plus 1 should be pulled to the right side. So 1 over 3 times of minus 1 plus yk minus z of k, and y of k plus 1 is equal to 1 over 3 7 plus xk plus 1 plus z of k, and third one is z of k plus 1 is equal to 1 over 3 minus 7 minus of x plus k plus y of k plus 1. Now multiply the right hand side by parameter w, and to the vector xk from the previous iteration multiply by a factor 1 minus omega. So when you write this, xk plus 1 will be equivalent to 1 minus omega times of xk plus 1 over 3 times of this. Similarly, y plus k is 1 minus omega times of yk plus omega times of 1 over 3 7 plus xk plus 1 plus z of k, and z of k plus 1 is equal to 1 minus omega yk plus omega times of 1 over 3 minus 7 minus of xk plus 1 plus yk plus 1. So initial guess is, that is x of y of z is, that is 0 0 0, and omega is equal to 1.25. So as we already told, for omega lies between 0 less than omega less than 2. So the for any initial vector, the SOR method converges, as we already seen it. Let us look at into the first iteration. So what I do is, the x1 I will keep it as it is, rest I will pull to the right side. So see that here what was done. So here xk plus 1 is all the terms to the right side. Similarly, yk plus 1 is equal to pull that side, and zk plus 1 is pull that side. Let us start with initial guess xyz is equal to 0. So the thumb rule is, if anything is not known as an initial vector, it is customary to assume 0 0 0 or 1 1 1 as the initial vector. So iteration 1 is x1 is equal to 1 minus 1.25 into 0 plus 1.25 into 1 by 3 minus 1 plus 0 minus 0, done. So if you simplify this, you get as minus of 0.4167, and y2 is equal to y1 is equal to 1.625. So then 1 by 7 times of this vector. Similarly, at the end you do multiply with. So x1 ultimately you get as minus of 0.4167, and y2 you get as 2.7431. So if you apply this similarly for Z1, you get the matrix like this. In the first iteration, you get like this. So that means in the first iteration, the value of x1 is minus of 0.4167, second y1 is 2.7431, third one is minus of 1.6001. So iteration 2 is, x2 is this value. So this is the value you get it, 1.4972, and y2 is equal to, you get 1.125, 2.7431 plus 1.25 into 1 over 3. So you do arrive this value. Similarly, Z3 you do get this value you do get it, Z3. So Z2, so y2, Z2, and you do have a third iteration, you look at over here. So whatever is known in the previously, we are substituting over here, minus of 1.25, 1 minus. So multiplied with this, and you are writing this. So simply what I am trying to do is, I am trying to express everything I am writing in terms of this factor xk plus 1, omega minus omega xk plus w times of 1 over 3 minus 1 plus yk minus zk. So it boils down to Gauss-Seidel whenever the values of omega happens to be 0. Omega happens to be 1. Okay, omega happens to be 1. Okay. So anyway, this will be 0, this will be 0, this will be 0. So x3 is done by this process. Similarly y3. So y3 also will be done in this process, and similarly z of 3 also will be done in this process. So in the iteration 4, x4 is equal to 1 minus 1.25 into this thing plus 1.25 into this thing. So ultimately you end up with a value 0.9428 as iteration 4. So y4 will become a value like this, and similarly z4 will become a value like this. So that means initially after 4 iterations you will have y4, we will have z4, and similarly if you look at into the iteration 5, so you get x5 as 1.0031, y5 as 2.0126, z5 as minus or 2.0026. So after 6 iterations we could able to arrive x5 as 1.0057, y5 as 1.998, z5 as minus 2.0025. Therefore, after 6th iteration, the solution of a SOR successive relaxation method will become like this. That is, x is equal to 1.0057, which is close to 1, y is equal to 1.998, which is close to 2, z is equal to minus or 2.0025, which is close to. So, using successive relaxation method, you would get much close to the true solution which is being expected. So, in the today lecture, what we learned is how iteration techniques can be applied for different examples like power method, successive relaxation method, and so many methods. So in the next class we are going to do some more examples. Thank you very much for being with this course. Thank you once again.